Okay, let's get started. We are looking at the properties of Z transform. We had seen linearity and time delay, and time delay we introduced the notion of fractional delay there. So, you can shift a sample by an amount that is not necessarily an integer number of samples, and we illustrated that with a MATLAB example where we had taken cos n pi by 5 and shifted it by 2.5 samples by applying e to the minus j 2.5 omega in the frequency domain. So, let us continue and look at the next property. So, this is exponential multiplication. Suppose you had x of n with Z transform x of z with this given region of convergence, then gamma power n x of n has Z transform x of z by gamma, and the ROC gets modified to this. The corresponding property for the DTFT is typically this: e to the j omega naught n times x of n. This has DTFT x of omega minus omega naught, and notice here I have used the x of omega notation because it is more convenient, and this is called as the modulation property. So, if you have to shift in the frequency domain, you have to modulate in the time domain. The proof is really very simple for this. So, we are looking at the Z transform of y of n, which is nothing but gamma to the n x of n. Therefore, y of z is n going from minus infinity to plus infinity, gamma to the n x of n z to the minus n, and this is written as x of n, and this can be written as z by gamma to the minus n, and this is indeed x of z by gamma, and the ROC is really R1 less than wherever z is there, you now have z by gamma. Therefore, z by gamma has to be part of the region of convergence, and this is commonly written as gamma times R1 less than mod z less than R2. So, this proves the property there. And as a simple example, suppose we start off with this x of n to be u of n. So, this is a special case of a to the n u of n where a is 1. So, this Z transform is clearly 1 by 1 minus Z inverse with mod Z greater than 1. So, starting from this we will get the Z transform of x of n to be r to the n cos omega naught n u of n. We will derive the transform of this. You can derive the transform of this from first principles, but we will use this property to derive the transform starting from the known Z transform of u of n. So, this is nothing but half times r power n e to the minus j omega naught n. Therefore, if you consider r to the n e to the j omega naught n u of n, so we will immediately apply the modulation property. So, here gamma is r e to the j omega naught. Therefore, this becomes 1 by 1 minus, wherever z is there you replace z by gamma. Therefore, this is z by r e to the j omega naught inverse, and you also have to take care of the ROC. So, this is now mod z by gamma has to be greater than 1, and this now becomes mod z greater than r, because gamma after all is r e to the j omega naught. If you take modulus, this thing disappears, and therefore, this becomes 1 by 1 minus r e to the j omega naught z inverse. Similarly, r to the n e to the minus j omega naught n u of n, this transform will be 1 minus r e to the minus j omega naught z inverse. ROC continues to be mod z greater than r, and you add these two factors, and then you also have a factor of half because it is cosine omega naught n. Therefore, r to the n cosine omega naught n u of n, this z transform if you take, if you add these two factors up multiplied by half, you will get 1 minus cos omega naught z inverse divided by 1 minus 2r cos omega naught z inverse plus r squared z to the minus 2. So, properties help you to get transforms quickly. You can plot the PoleZero plot for this x of z, right. So, x of z is, you have z square minus 2r cos omega naught z plus r squared, and this is z times z minus r cos omega naught. So, there is a trivial 0, and there are two poles. Because we have simplified this, you need to find the roots of this, but really the factors are 1 minus r e to the j omega naught and 1 minus r e to the minus j omega naught z inverse. These are the two factors. Therefore, the poles are at r e to the j omega naught and r e to the minus j omega naught. These are where the poles are. Therefore, you have two complex conjugate poles at radius r. So, here I have chosen r to be less than 1, just for illustration. So, this is the circle of radius r where the poles are, and the 0, 1 0 is at z equal to 0, which is the trivial 0. The other 0 is at r cos omega naught, therefore, it is right here. It is on the line, vertical line joining the two poles. And if r were 1, these poles will lie on the unit circle. If r were greater than 1, these poles will lie outside the unit circle. Here I have shown r to be less than 1. Similarly, you can work out the transform of r to the n sin omega naught n u of n along similar lines. Suppose you had gamma to be minus 1, this will be x of minus z, because it is x of z by gamma, gamma is minus 1. The corresponding dTFT is this is the same as e to the j pi n. If it is e to the j omega naught n, it is x of omega minus omega naught. Omega naught happens to be pi, therefore, this is this, and this is also the same as x of omega plus pi, because minus 1 to the n is e to the plus or minus j pi n. Let us look at what this exponential multiplication does in the z domain. Suppose z naught is a 0 of x of z. So, this implies that x of z naught is 0. Now, if you consider y of n, which is gamma to the n x of n, this z transform is y of z. So, this is x of z by gamma, just repeating the property here. Now, what is y of gamma z? Y of gamma z is nothing but x of z. Wherever z is there, replace z by gamma z. So, this implies y of gamma z naught equals x of z naught, but x of z naught is 0. Therefore, gamma z naught is a 0 of y of z. The implication of this is that, remember, gamma is in general a complex constant, z naught is a 0 in the complex plane. Therefore, gamma z naught means you are taking the original 0 z naught and scaling it by magnitude of gamma and rotating it by the angle of gamma. Therefore, exponential multiplication causes scaling and rotation of the roots in the z plane. Therefore, so geometrically this scales and rotates the roots in the z plane. Note that I had started off by illustrating this by showing that if z naught were a 0, the new 0 for the exponentially multiplied sequence is gamma z naught. So, this scaling and rotation is not just limited to the zeros, it is limited to both poles as well as zeros, because this is after all x of z is of the form p of z over q of z. So, this implies the transform of gamma to the n x of n is y of z, which is nothing but x of z by gamma. So, this in turn is p of z by gamma by q of z by gamma. So, this means that both poles and zeros get scaled and rotated. Again, this is not just an idle property, in the sense that it is not just mathematical. It has an important application in, say, for example, like a speech coder. In speech coding, what they do is they do perceptual weighting. Okay. So, perceptual weighting is used, and the motivation for this is, after all, for coded speech, the final judge of what has been coded is your ear, and ear has some special properties. It has what is called masking. So, if you have one tone that is played, you will hear it. If there is another tone, by tone we mean a pure sinusoid, if that tone, the next tone that is played along with the first tone, say it is weaker, that is, it is smaller in amplitude, but if you adjust the frequency such that the weaker tone's frequency is close to the stronger tone, if it comes close enough, you will not hear the weaker tone. The weaker tone will be perceived only if it is reasonably away in frequency from the stronger tone, and this is what is called as the masking property of the ear. So, what they do is, when they quantize and when there is this error spectrum that is there, if you shape the error spectrum such that you put error energy more in frequencies where there is more energy in the signal itself. In those cases, the error will be masked. So, these perceptual weighting, these are very heavily used in your actual speech coders. So, when you are able to compress your music to much smaller values compared to your raw sampling that is used. If you say you sample it at 16 kilohertz, and even if you use 16 bits, or if you sample it at 44.1 and use 16 bits, that is a lot of samples and bits, and the file size will be very large. On the other hand, if you compress it using say MP3, you get significant reduction in file size, that is the storage, but you do not perceive too much of a difference. And this is because all these psychoacoustic properties are exploited, and the error spectrum is shaped so that the error is distributed in regions of the spectrum where you do not hear it. All right. So, in that context, this perceptual weighting is used, and in speech the vocal tract, which is the technical term for the mouth, and that is modeled as an all pole filter, and this all pole filter notationally is typically called as A of Z. It is modeled as 1 over A of Z, and A of Z is estimated, and the perceptual weighting that is used is A of Z by gamma 1 by A of Z by gamma 2. So, this is the perceptual weighting filter that is used, and one of the commonly used speech coders is AMR, adaptive multi-rate, and in AMR gamma 1 is 0.96, gamma 2 is 0.6. And typically A of Z is 1 plus AP Z to the minus P, and these coefficients are estimated A1 through AP, and for the perceptual filter you will multiply this sequence. So, in the time domain this is nothing but 1, A1, A2 up to AP, and this time domain sequence is multiplied by gamma to the n, where gamma is 0.96 and 0.6 and so on. And using this perceptual weighting filter is created, and this is used to improve the quality of the speech coders. So, this property has very significant practical use in speech coding.